Hello everyone. Today I'll be discussing a subject that is very near and dear to my heart, which is correctly rounded math libraries. I've been doing research in this area since the start of my PhD, and hopefully by the end of this talk, all of you can share some of my excitement towards this topic. Math libraries are ubiquitous across various domains of programming. For example, if you're working on a machine learning project, you would use the exponential function provided by your favorite math library to implement a sigmoid function. Given the degree to which we rely on math libraries, it is fair to inquire about their accuracy. Unfortunately, many of the functions found in mainstream math libraries produce inaccurate results for several inputs. Of course, programs can tolerate different levels of accuracy depending on what the end goals are, so I'm not going to make any claims to catastrophe here. However, in a world where different functions in different libraries produce different results, your program can exhibit different behavior depending on what hardware and/or library is available. For the purposes of program portability and reproducibility, we need standardization. Standardization requires a notion of correctness. Now, for the vast majority of their inputs, elementary functions, like the ones you see on the slide, produce irrational values that are not exactly representable with finite precision. So under finite precision, what should correctness entail? The RLIBM project argues that correctness should entail correct rounding. Given a function and an input, the correctly rounded result is the output of the function evaluated in infinite precision, directly rounded to some target representation using some rounding rule. Here is a visual illustration. Suppose v1 through v3 represent three consecutive values in a floating point format, let's say the 32-bit float. And let's suppose for a given input x1, log of x1 evaluated at infinite precision is between v1 and v2, with it slightly being closer to the latter value. Under round to nearest, log of x1 will round to v2, which would make v2 the correctly rounded result. A function that can produce correctly rounded results for all its inputs is a correctly rounded function. A math library composed of such functions is a correctly rounded math library, and RLIBM believes that that is the gold standard for reproducible numerical programs. Now that I've established our notion of correctness, I'll provide some details on how math libraries actually implement elementary functions. Math libraries approximate elementary functions using polynomials. The cost of evaluating a polynomial is roughly proportional to the number of its terms, so lower degree polynomials are preferable. Unfortunately, low degree polynomials that can accurately approximate over a wide domain, such as the full dynamic range of 32-bit floats, are likely infeasible for many elementary functions. However, low degree polynomials can be accurate over smaller intervals. To enable the usage of low degree polynomials with low evaluation overheads, math libraries transform their inputs to values in a smaller domain as a first step. This process is referred to as range reduction, and the transformed versions of the inputs are referred to as the reduced inputs. Now, the output of a reduced input may not be the same as the output for the original input. As such, these reduced inputs require operations that map their outputs back to the target range of the original domain. And these operations are collectively referred to as the output compensation. Range reduction and output compensation are critical components to implementing any elementary function, and I will come back to these topics when I later discuss the implementation of trigonometric functions. Polynomial approximations are by definition approximations, and therefore they inherently carry some amount of approximation error. Evaluating polynomials at finite precision would induce some amount of numerical error as well. The most conventional approach to implementing correctly rounded elementary functions is minimizing these errors for the purposes of replicating the target real functions as accurately as possible. Now let's suppose that you are a math library developer working on implementation of the log function. Given an input, how can you ensure that your approximation can produce the correctly rounded result? Here's an illustration of the intuition behind RLIBM's proposed answer. So like before, let's suppose v1 through v3 represent three consecutive 32-bit floats. And let's suppose that for a given input x1, log of x1 rounds to v2 under round to nearest, making v2 the correctly rounded result. So normally, math libraries would evaluate their functions in higher precision compared to whatever is available in the final target representation. So let's suppose that your approximation outputs 64-bit doubles. Notice there is going to be a range of 64-bit double values around v2, represented by this green box, that all round to v2 under round to nearest. This green box represents what is referred to as the rounding interval for v2, and the bounds on such intervals are referred to as the rounding decision boundaries. As long as your approximation's output is within this rounding interval, your approximation's output can be rounded to the correctly rounded result. So how large are these rounding intervals? For each real result, the size of the rounding interval is 1 up, or unit of least precision. You can think of the up for any real number as the distance between the two closest numbers in the target representation. So in this example, the up for log of x1 will be the distance between v1 and v2. The key takeaway here is that your approximation can incur up to 1 up of error relative to the real result and still produce the correctly rounded result so long as its output is within this rounding interval. Now let's contrast this behavior against approximations that produce values outside the rounding interval. So let's suppose that you were able to obtain a very accurate approximation of the log function that induces only a small amount of error for the input x1. Now, even in spite of the small amount of error, it is still possible that your approximation's output is on the wrong side of the rounding decision boundary. In such a case, your approximation will be unable to produce the correctly rounded result. This example shows that rounding intervals offer a much larger degree of freedom of tolerable error as it pertains to correct rounding than what is available under conventional error minimizing approaches. This large degree of freedom for error can allow for low-degree polynomials with low evaluation overheads. And this example also shows that when it comes to correct rounding, the real results are ultimately means to an end and not the ultimate objectives themselves. Taking all of these details into account, the RLIBM project makes the following proposal. For the purposes of developing fast correctly rounded elementary functions, you should directly approximate the correctly rounded results rather than the real results and use the rounding intervals as the degree of freedom to do so. Now you might be asking yourself, don't you need the correctly rounded results to identify the rounding intervals? And if you pull on that string, it seems like we're making the claim that to produce correctly rounded results, you need to have the correctly rounded results. So the snake is starting to eat its own tail here. Now, I'd like to clarify at this point that producing correctly rounded results onto its own is not RLIBM's final value proposition. There exist libraries like MPFR that can produce correctly rounded results for any function they support for any arbitrary target representation. Despite their flexibility, however, the functions in such libraries may be a bit too slow for programs operating under more performance-critical settings. Using these libraries as oracles, RLIBM aims to identify a more optimized approximation of their results so it can serve as a faster point of reference for developers while remaining correct. In short, RLIBM's motto is, give us your results, and we'll find a more efficient way of reproducing them. So here is an overview of the steps that RLIBM takes towards accomplishing this goal. As I alluded to earlier, RLIBM begins by generating the correctly rounded results for a given function using an oracle generator like the aforementioned MPFR library. And using the correctly rounded oracle results, RLIBM identifies the appropriate rounding intervals. Now, I explained earlier that a polynomial can produce correctly rounded results so long as its outputs are within these rounding intervals. So the bounds on these intervals can be thought of as linear constraints on the expected outputs of the desired polynomial. RLIBM encodes these constraints into a system of linear inequalities, and in doing so, it transforms polynomial generation into a linear programming problem. It then uses an LP solver to identify the appropriate coefficients that would allow the final polynomial to produce values within the target rounding intervals. In all my examples up to this point, I've been primarily referring to 32-bit floats. Over the past several years, new representations like bfloat16 and TensorFloat32 have emerged to explore different trade-offs in performance and precision. Now, given these new representations, one might ask, can I round the correctly rounded 32-bit float result and obtain, let's say, the correctly rounded bfloat16 result? And the answer to that question, unfortunately, is no. Using the correctly rounded 32-bit float result in such a manner would constitute double rounding, as you will be rounding an already rounded value. Double rounding can lead to incorrect results when the real result and the correctly rounded result for an intermediate representation end up in different rounding intervals of the final target representation. On the other hand, having to support each and every representation using a separate implementation can lead to massive code load. Code maintenance becomes a major challenge for math library developers, and math library users would have to expend a lot of time into identifying which implementation is appropriate for their intended representation. Given these challenges, The RLIBM project has identified a remedy for the issues involving double rounding in the form of the non-standard round-to-odd rounding mode, or RNO for short. Under RNO, each row result is rounded to the nearest number in the target representation with an odd bit pattern. Specifically, RLIBM has discovered that the correctly rounded n+2-bit result under RNO is guaranteed to round to the correctly rounded result for any representation with up to n bits and for any standard rounding mode. By directly approximating the correctly rounded 34-bit RNO results, the RLIBM project has become the first library that provides for each function that it supports a single implementation that can produce correctly rounded results for all representations with up to 32 bits and for all standard rounding modes. And for those of you who are interested in the details behind just exactly how this technique works, I'd highly recommend reading the POPO 2022 paper. Now, I consider all of these advancements to be fantastic, but they were made prior to my joining the project. So now I get to talk about my specific contributions. When I started my PhD, the RLIBM project had been ongoing for a couple of years, but did not yet support trigonometric functions. As such, my advisor gave me the task of implementing a correctly rounded sine function as my first research project. Now, given this task, I couldn't help but ask myself, RLIBM has exponentials and logarithms. What makes trigonometric functions so special? With that question looming over me, I did my best to study up on the topic. Early into my investigation, I learned that to implement elementary functions, you need to perform range reduction. Through range reduction, you transform your inputs x to reduce inputs x prime in a smaller domain that can make accurate approximation using low-degree polynomials feasible. I also learned that sine is a function that's amenable to range reduction because it's periodic over intervals of size 2 pi. Normally, if you want to take a number a and extract from it a value bounded by some other number b, what would you do? You perform some type of modulo operation. You can subtract from x the product of 2 pi and k, where k is the integer nearest to x over 2 pi, to obtain x prime between negative and positive pi, and this would constitute a valid range reduction. I explained earlier that every range reduction has a corresponding output compensation, and you can identify what the appropriate output compensation should be by rewriting x in terms of x prime. So sine of x will be the sine of 2 pi times k plus x prime, and given that sine is periodic over 2 pi, sine of x would just be sine of x prime in this case. And the output compensation is just the identity function. Through this range reduction and output compensation, you are able to reduce the task of approximating sine over all 32-bit float inputs to just approximating sine over values between negative and positive pi. Now, the interval between negative and positive pi may still be too large to obtain an accurate low-degree polynomial. So you can use variants of this range reduction strategy to bound the magnitude of your reduced inputs by any factor of pi. In my case, I decided to perform a modulo operation with pi to obtain reduced inputs between negative and positive pi over 2. The corresponding output compensation is as shown here. The range reduction described on the slide can be repurposed for cosine and tangent as well, and those functions just require different output compensation functions. And like before, through this range reduction output compensation, I'm able to reduce the task of approximating sine over all 32-bit float inputs to just approximating cosine and sine over values between negative and positive pi over 2. So at this point, I have a range reduction and an output compensation. All I need to do is concretize the exact steps required to compute all the values involved. And this can be done through a series of rewriting. The input x can be rewritten as the product of pi and x over pi. X over pi can be expressed as the sum of k, its nearest integer, and r, which would be the corresponding fractional portion. Through a sequence of rewriting, you're able to conclude that x prime is the product of r and pi. So for my very first range reduction implementation, I decided to directly translate all these steps into a double precision program. So for my first range reduction implementation, I represented pi and its inverse using their nearest double precision values, and these numbers are widely available in libraries like glibc. The range reduction strategy starts off by multiplying x with the inverse of pi. Multiplication with the inverse is done here because multiplication is cheaper than division. Next, the range reduction breaks down x over pi into its nearest integer k and the corresponding fractional portion r, before multiplying r with pi to obtain the desired reduced input x prime. Looking over this entire procedure, all the steps seem to make sense at face value. But when I actually applied this range reduction, I noticed that the reduced inputs ended up becoming 0 for all large inputs x. Now, my range reduction is doomed to fail at this point because you can't reconstruct all possible values of sine just using cosine and sine of 0. I double-checked my program and everything seemed to check out algebraically, so I found this behavior to be very odd. And naturally, I reported my observations to my advisor. My advisor, who had already been looking into this topic, then guided me to read the seminal paper on trigonometric range reduction by authors Payne and Hennig to figure out what is going on. So Payne and Hennig explained that when the input is very large, the leading bits of 1 over pi won't produce any fractional bits in x over pi. So in my case, I was representing 1 over pi using its nearest double precision value, which only has 53 bits of precision. You can imagine that when the exponent of the input is 70, 80, 90 or larger, that none of those 53 bits will produce any fractional bits for the subsequent product. Payne and Hennig add that in order to perform range reduction accurately for all 32-bit float inputs, you would need approximately 200 bits of 1 over pi. Now, having to perform operations while maintaining so many bits, especially in finite precision, can take a huge toll on the performance of the final implementation. And that is precisely why so many libraries forego some degree of accuracy for the sake of performance. Now things were starting to make sense as to why RLIBM did not yet have correctly rounded trigonometric functions. Now, the key insight offered by Payne and Hennig is that you don't need all those bits of 1 over pi for each individual input x. I'll provide the intuition as to why by referring back to my range reduction and my output compensation. Using the periodicity of sine and cosine, you can rewrite my output compensation as follows. Now, based on this expression on the bottom right, you can make the following conclusion. For the purposes of reconstructing the final value for sine x, the least significant bit in k, the integer nearest to x over pi, is the only integer bit in x over pi that matters. Based on this observation, Payne and Hennig provide the following analysis. For each input, the bits of 1 over pi can be split into the following 3 groups. Group J is composed of the lower order bits of 1 over pi that will contribute to the fractional portion of x over pi, which I've been referring to as r. Group I is composed of the single bit that contributes to the least significant bit in the integer portion k. Group H contributes to the bits that Group H is composed of the bits that contribute to the multiples of 2 in k. As such, the partial products stemming from these bits will not impact the final output, and you can skip these bits in their entirety without impacting the final result. Payne and Hennig conclude that you can identify which bits to skip for a given input using the input's exponent. So using these crucial insights, I went ahead and implemented an updated version of my range reduction strategy. So for this range reduction strategy, I represent 1 over pi using its first 196 bits, which I obtained from MPFR. I spread these bits across 7 doubles so that each double contains a 28-bit piece of 1 over pi. Why 28? Every 32-bit float input is expected to have 24 bits of precision. So by distributing the bits in this manner, I can ensure that the partial products can be exactly represented as doubles without any loss in precision due to rounding. In addition to these doubles, I also maintain an array of integers. Each integer represents the exponent of the least significant bit in the corresponding piece of 1 over pi. And using these exponent values, I can identify for each input the first relevant piece of 1 over pi using the following iterative search. So let's say that the input can be expressed as an integer multiple of 2 to the power of e, where e represents the exponent of the least significant bit in the input. When the sum of e and the exponent of the least significant bit in a given piece of 1 over pi exceeds 0, you can conclude that the partial product stemming from said piece is not needed for reconstructing the final output. So here's an illustration of how the search would work in practice. Let's suppose that the input has an exponent of 90. Based on this loop condition, we are able to conclude that the first 3 pieces can be skipped without impacting the final result. And when this loop terminates, you are able to conclude that the 4th piece is the first relevant piece of 1 over pi, and you can compute partial products using the remaining pieces to proceed with your range reduction and output compensation. Using this updated range reduction strategy, I was successfully able to develop correctly rounded implementations of sine, cosine, and tangent. However, the performance of these new functions was a bit lagging compared to that of their counterparts in other math libraries. And we attribute this performance or lack thereof to this iterative search. Now, this iterative search allows us to bypass any superfluous computation. However, it's not very amenable to parallelization. As such, this search is a performance bottleneck onto its own. If we were able to compute the full product using all the bits of 1 over pi we're maintaining, using only a small number of operations without any loss in precision, we wouldn't need this search to begin with. Integer representations offer a larger amount of precision compared to their floating point counterparts, and as such, we decided to explore an integer-based alternative. For this integer-based range reduction strategy, we represent the precision bits of 1 over pi using 3 64-bit integers. Now, these integers contain only the precision bits, so we need to keep track of the associated exponents implicitly. We also represent the precision bits of the significand of the input as a 64-bit integer as well. Using these integers, we compute the partial products and store the results as 128-bit integers. 128 bits allow us to compute the partial products without any loss in precision due to rounding. Finally, we accumulate the partial products to obtain the precision bits of the final product, which we then spread across for 64-bit integers. Now, at this point, we don't have any explicit information on the exponents associated with the different bits in the final product, yet we still need to be able to differentiate the integral bits from the fractional bits. The core element of this strategy is using the information we have on the exponents associated with the different pieces of 1 over pi to draw the necessary inferences. So I'll provide an illustration of what I mean. Let's suppose that the input has an exponent of 70. Using what we know about the exponents associated with the different pieces in 1 over pi, we can conclude that the exponents associated with the least significant bits in the different pieces of the final product are as shown here. Using these exponent values, we are able to conclude that the binary point, which immediately follows exponent 0, is contained in the second lower order piece of the final product. Naturally, the lower order integral bits will be spread across the second and third pieces, while the fractional bits will be spread across the first and second pieces. Lastly, using these exponent values, we're able to shift the different pieces accordingly to obtain a single integer representation of the integral portion of the final product, as well as a single integer representation of the fractional portion. And to anyone who's interested in just exactly how we compute the specific shift amounts, I'd welcome you to read the paper we submitted to VSS. So like before, using this integer-based range reduction strategy, we were successfully able to develop correctly rounded implementations of sine, cosine, and tangent. Now, we invested a fair amount of time into investigating this integer-based range reduction. So we wanted to confirm that it actually yielded a meaningful performance boost. So here's a graph showing the performance speedup of the integer-based implementations over their floating point-based counterparts. And as the bar on the far right would show, the functions that use the integer-based range reduction achieve a near 20% speedup over the floating point-based alternatives. And I'd like to add that using the integer-based range reduction, we were able to achieve a meaningful speedup over functions in other math libraries as well. In closing, the presence of irrational values like pi and its inverse can make accurate range reduction for trigonometric functions very challenging. In order to perform range reduction accurately for all inputs, you will need to maintain 1 over pi using a large number of precision bits. Performing operations with so many bits and finite precision can have a negative impact on the performance of the final implementation. Now, integer representations offer a much larger amount of precision compared to their floating point-based counterparts. Using the large amount of precision offered by these integers, we were able to identify an integer-based range reduction strategy that achieves sufficient accuracy while keeping the final performance overheads minimal. Through this integer-based range reduction strategy, the RLIBM project was successfully able to develop fast, correctly rounded implementations of trigonometric functions after years of attempting to do so. On that note, I would like to welcome anyone who's interested in actually trying out our functions, and I thank everyone for their time and attention.